Why is there so much space inside an atom? An atom consists of a negative electron, a positive nucleus, and apparently a lot of nothing in between. So why don't electrons fall into the nucleus, if opposite charges attract? Hi, I'm a physicist, and the short answer to this is there isn't much space in an atom, because atoms don't work like this, but like this. Quantum mechanics says that electrons don't fall into the nucleus due to their nature. But what is their nature? What does this mean? What are those blobs supposed to tell us? How do atoms actually work? I'll explain how we're gonna tackle all this in a second, but now let's jump right into it. Classical physics tells us that atoms are electrons circling a nucleus. But as a consequence, every atom should collapse instantly. In short, electrons should constantly lose energy, simply because they are circling the nucleus. And as they lose energy, they should be pulled closer and closer to the nucleus because they just can't resist the attraction anymore. Well, lucky us, that's not what happens. To understand what actually happens, we need to figure out how atoms, and especially their electrons, work. Or at least how we currently think they work. Our current understanding is based on quantum mechanics. In my last video, I gave an intuitive introduction to quantum mechanics, the one I wish I had. This here is the second video in a mini-series where I try to answer our biggest questions about this super confusing topic. So if you have any questions or thoughts, please drop them in the comments below. Thanks! And don't worry, of course you can watch this video by itself. So, what are electrons and atoms up to? That was a huge question in the early days of quantum mechanics. And it started with the energy of atoms. So, we'll start with this energy thing as well, because it's a good introduction. It sets us up to understand how atoms and their electrons actually work. How can we know anything about the energy of an atom? Well, we can measure what happens if an atom loses energy. An atom mainly loses energy when its electrons lose energy. An electron loses energy by emitting a photon. A photon is nothing else but light. It has a wavelength, which is directly related to its energy. So if we take the simplest atom, a hydrogen atom with only one electron, and measure the light coming out of it, we know how much energy the electron lost. Therefore, we measure the wavelength of the photon, calculate its energy, and since energy is conserved, this is exactly the energy lost by the electron. Doing this measurement, you notice something odd. Something you probably heard before. The light has only certain wavelengths, which means it has only certain energies. So if an atom loses energy, it loses these fixed amounts of energy. So without knowing anything else about the atom's energy, we now know that it cannot change by any random amount. It can only change by fixed amounts. It jumps. That's a quantum jump. The smallest possible change in energy an atom can undergo. Because there is this smallest possible change in energy, the atom cannot just have any amount of energy. The energy of an atom can only take specific values, which we call energy levels. If you ever stumbled across a picture like this, that's what the picture is trying to tell you. That the atom can only have one of these specific energies, these energy levels. Okay, so an atom cannot continuously lose energy. This means an electron cannot continuously spiral into the nucleus, because then it would continuously lose energy. Okay, but why can't the electron just jump closer and closer to the nucleus while it loses discrete amounts of energy? Because of how atoms and electrons actually work. So, how does an atom actually work? You probably already heard that an atom does not look like this. The electron is not on a specific path around the nucleus. But as we already know, the total energy has indeed a specific value. So the electron does not take a specific path, but this doesn't mean that we don't know anything about where the electron is. Actually, the specific energy of the atom does influence the electron's movement and therefore its location. That's why the specific energy tells us where the electron is most likely going to be if we measure it. That's what these pictures are supposed to tell us. When the energy is at its lowest, the electron is most likely somewhere in this blue blob, with 90% probability. So don't think of electrons orbiting the nucleus at different distances. Think of electrons having different fixed energies, and from these energies follow region where the electron will most likely be. Now, these blobs are called atomic orbitals. I will come back to them and explain in more detail how they come about. But first, maybe you've already noticed that if we go one energy higher up, we have 4 different blobs, 4 different orbitals. We have a sphere similar to the lowest energy level and 3 times this thing orientated differently. This is because not only the energy, but also the electron's angular momentum affects where the electron is likely to be. If the angular momentum is 0, we get a sphere. If the angular momentum is 1, we get this thing. This angular momentum can point in some direction, so we need one of those for each of the 3 basic directions. That's why the next energy level has 4 orbitals. Because with this energy, the electron can have angular momentum as well, and this points into some direction in space. If you ever come across these names, the numbers indicate the energy level, the letters indicate the value of the angular momentum, and these indices its direction. The letters come from old terms that we now know don't make sense. Okay, so the location of an electron inside an atom is somehow described by those orbitals. Each orbital belongs to a fixed amount of total energy, and this is the orbital for an atom with 1 electron in its lowest energy level. Just like an apple that wants to fall down to minimize its potential energy, an electron wants to be in the lowest orbital. Why in the lowest orbital and not in the nucleus? Well, actually, they are partially in the nucleus if they are in the lowest orbital. We will come to that. But why don't they fall completely into the nucleus? The closer the electron is to the nucleus, the less space it takes up, and we know from Heisenberg's uncertainty principle that less space means higher momentum or higher velocity. So it gets so fast it basically kicks itself out of the nucleus again. Put differently, the lowest orbital is usually the sweet spot when it comes to energy. Okay, but if that's the sweet spot, why don't all electrons just jump into the lowest orbital? As we'll answer this, we will also discover that an atom is not just mostly empty space. So, how do electrons actually work? We must describe electrons quantum mechanically, because as we've seen, a classical description would end up with this. In my last video, I explained the key features of quantum mechanics. One is, what we see when we look at the world is quite different from how we describe the world when we're not looking at it. If we look at an electron, we will find it to be in one place, for example here. But when we're not looking at it, we're talking about it in terms of probabilities. We say it has a certain probability to be here, but also to be here or here. So we can't predict that we will find it here, but we can calculate the probability that we will find it there. That's how we get these images. Let's say there are 100 dots, then each dot represents a 1% chance of finding the electron at this distance from the nucleus. So here there are a lot of dots. There's a high chance of finding the electron within this distance from the nucleus. Maybe you notice that there's also a chance of finding the electron in the nucleus. That's odd. It will make a bit more sense in a moment. Here there's also a high chance of finding the electron within this distance, but only at certain angles. The angular momentum of the electron makes these directions less likely. Now you draw a line around 90% of the dots and you get the blobs. The thing is, those probabilities are not there due to us not being able to make good predictions. They are fundamental to quantum mechanics. Predicting probabilities is the best quantum mechanics allows us to do, as opposed to classical physics, that in principle always allows us to make precise predictions. If we only predict probabilities in classical physics, that's due to things like not having all the necessary information. But in quantum mechanics, that's not due to lack of information. Predicting probabilities is a fundamental part of quantum mechanics. So, instead of thinking the electron is here but we cannot precisely predict that, we can only predict that it's most likely here, think of it this way. The electron is in all of these places, not just in one. Where there are more dots and the probability is higher, there is somehow more of the electron. If that's confusing to you, well, that's because it is confusing. If this video clears some of your confusion, please leave me a like. Thanks. So, it's totally normal to be confused. Also because if we measure it, we will find it at a certain spot. But remember, what we see when we look at the world is quite different from how we describe the world when we're not looking at it. When we look at it, we find it in one place. But we describe it to currently be in a mixture of all places. Think of a cloud, which is in multiple places at once, but has parts where it's thicker, so there's more cloud, and parts where it's thinner. Now, looking at the orbitals, the blobs, we can view them as electron clouds. And now the electrons take up a lot of space inside the atom. So the electron in the lowest orbital fills all of this. It's even partially in the nucleus and also stretches into infinity. But at infinity it's really thin. The electron cloud is mainly here. Importantly, if there is already an electron filling an orbital, there is no space for another one. So that's why they are not all in the lowest orbital. Well, actually, you can fit 2 electrons in one orbital. One that has spin up and one that has spin down. But there can only be one of each type in one orbital. This is Pauli's exclusion principle. 2 or more identical electrons cannot simultaneously occupy the same quantum state, for example, the same orbital. There are only 2 types of electrons, spin up or spin down. So if they have the same spin, they are identical. Okay, so this explains why all electrons don't just jump into the lowest orbital. They can't. They can't pile on top of each other. Actually, Pauli's exclusion principle not only holds for electrons, but for all fermions. Fermions are the fundamental particles that make up you, me, everything. The other type of fundamental particles are bosons, which don't make up anything, but are responsible for the forces that hold stuff together. Bosons can pile on top of each other, fermions can't. Fermions take up space. 2 or more identical fermions cannot simultaneously occupy the same quantum state. Okay, so electrons in atoms occupy these blobs called orbitals. They take up space, so there's only room for 1 electron of a kind in one orbital. Each orbital belongs to a certain fixed amount of energy and a certain angular momentum of the electron. The lowest orbital is the most attractive one, in the opinion of electrons. But it's important to note that the model of atomic orbitals is just a description of reality, not reality. For now, it is our best description, if you add in some complications with multiple electrons I did not mention. But yeah, importantly, it's just a description. And this is just an attempt to visualize this description. I don't know how an electron inside an atom looks. I mean, as soon as we look at it, it changes. But I think the picture of an electron cloud is a good way to gain an intuition. If you want to gain an intuition for how quantum mechanics works, check out my last video. Thanks for watching. Have a wonderful day.